Good afternoon, everyone. My name is Jianwei Liao. I come from Southwest University of China. Today, I'm going to talk about a flexible I/O arbitration framework for netCDF-based big data processing workflows on high-end supercomputers. Actually, this work was done when I had postdoc position at RIKEN. Here is outline of this presentation. First, I will talk about motivation example of SCALE-LETKF. Then I will show you the proposal of I/O arbitrate middleware. After that, I will simply talk about our future work plan. Okay, let's move to the first part. Our motivation example is SCALE-LETKF, which is a weather forecast application and used for predicting the unexpected heavy rain in local areas. It has two components. One is called SCALE, which is used for data simulation. Another one is called LETKF, which is used for data assimilation. Both components have some data dependency. So normally, the simulation processes writes the output to the global file system, and which data are supposed to be read as input data of data assimilation processes. And the assimilation process do some computations. The outputs will be flashed to the global file system again. Actually, this part of data are supposed to be read by the simulation processes as input data in the next round of iteration. In order to speed up the prediction, for predicting the unexpected sudden heavy rain, so we are supposed to finish one cycle of iteration within 30 seconds. That means the time required for simulation, assimilation, and the time required for disk I/O operations. So our task is to reduce the disk I/O time as much as possible. This slide shows the I/O patterns in SCALE-LETKF. In every 30 seconds, and each weather simulation generates 17 gigabytes data, and that means 1.7 terabytes data in total if we have 100 ensemble cases. Actually, for the assimilation side, it has very similar amount of data, 1.7 terabyte data in total. Actually, it is a big data application. Here we have a figure about the breakdown time analysis when we run SCALE-LETKF with a real case by using different numbers of computer nodes. Okay. We can see that when the number of computer nodes is getting large, is getting more, actually excuse me, I'm a little nervous. So when the number of computer nodes is getting more, the execution time is getting down. That's reasonable. However, the I/O time, which is labeled as X in each cases, keep unchanged. That means if we have more computer nodes, the I/O take more proportion of total time. So we want to change the I/O behaviors and to reduce the time required for I/O operations. Here is a current I/O behavior, and all data are exchanged by using global file system. So if we can introduce an I/O arbitrate middleware and to support transferring the data from one side to another side, I think the time required for exchanging the data will be reduced significantly. The benefits something like this: if we can reduce the I/O time, then we can leave more time for computations, for simulation and assimilation. To this end, we have proposed the arbitrator middleware. Then I will talk about details. Before I talk about the technical points, I will show you two design issues when we design this middleware. The first one is about what level of the abstraction. We are working on the netCDF layer, but other layers might be possible. The second design issue is about what kind of communication facility is used to transfer the data. So we are now using MPI, but LLC will be used in the future. LLC the low-level communication layer, which will be deployed in the post-K supercomputer. The first technical point is about how to build communication environment. So first, we can say from this figure, first, our assimilation process will open a port. After that, the simulation processes can connect to this port. After that, both kinds of processes can communicate with each other by using our intercommunicator. Here, I list some critical interfaces in MPI library, which are used in our middleware. Okay, I'll just skip the description of these interfaces. The second technical point is about buffering data in memory. Actually, we have modified the netCDF library so that on the side of simulation, all write requests will be intersected, and the write contents will be buffered in our memory buffer instead of going to the disk. So when the netCDF file is closed, actually the data will be sent to the destination assimilation process. So for the assimilation process, all read requests will be responded with the data cached in the memory buffer. So from this demonstration, we can see that the I/O operations are not needed anymore. The third technical point is about the two schemes of data transfer. We provide two schemes of data transfer. The first one is called synchronized data transfer. That means all data is transferred to another site when the netCDF file is closed. Another mechanism is called asynchronous data transfer. That means part of data will be transferred to another site during the computation. So it enables the overlapping computation and the data transfer. We call, when the netCDF file is closed, only the dirty data will be transferred to another site. So we can see from this figure, compared with async data transfer, compared with sync data transfer, async data transfer can save much more observed transfer time. We have conducted several experiments with scale on K. We used 3 real cases for regional weather analysis. And I will not talk about the details about benchmark, but we care about the size of involved data in the test cases. Here, I list the size of involved data in the selected test cases. For instance, in text case 3, if the ensemble size is 100, the size of total data is more than 500 terabytes. Okay, these are benchmark specifications. I think the climate people may understand. Actually, for me, I don't understand them quite well. First, I recorded the observed time by using the data transfer schemes offered by our middleware. Those three figures show the experimental results. The x-axis shows the number of ensemble cases. So the y-axis shows the transfer time in milliseconds. From the results, we can see that compared with sync data transfer, okay, blue lines, the async data transfer can indeed reduce the transfer time by more than 60%. That is because async transfer enables overlapping the computation and data transfer. After that, we measured the time required for writing by scale and reading by LTCF processes. Here, I want to explain that in the middleware, the I/O time indicates the time required for memory operations and the time for observed transfer time. Those three figures show the results. We can see that the mechanism of directed transfer can reduce the I/O time by more than 80%. Also, there is another interesting clue in these figures. We can see that the blue line and the red line are the results by using sync and async data transfer schemes. But they have very similar I/O time. This is because both of them have the same time for memory operations. And memory operations take a major part of I/O time. Consider about this case in the real cycle. The I/O time is longer than 30 seconds. So that means we cannot meet the deadline if we use file I/O-based data exchange. We also report the I/O data throughput, and we can say the facility of direct transfer can achieve more data throughput by up to more than 30 times. Another attractive finding is that the improvements are getting remarkable while the ensemble size is getting larger, that in case more data are required to be processed, which indicates that our proposed mechanism scales quite well. Finally, it's about future work. Actually, this work schedule was made in June 2016. So when I left RIKEN, now our group have finished the first two steps. I think the work has been done by Tanya-san. Actually, please refer the poster 1-12, and you can find more details. In the near future, I think our task is to implement a mechanism to enable the middleware for supporting accurate data transfer. That means data redistribution is not needed on receiver side by using high-level information provided by netCDF library. Thank you very much.